So today I'm going to be explaining why in circular motion the acceleration is equal to the velocity squared over the radius. So before we start, these are just some key equations you're going to need throughout the process. The acceleration is equal to the change in velocity over time. I'm sure you already know this. And now the angular velocity, which is radians per second and denoted by lowercase omega, is going to be equal to the change in angle, or delta theta over t, and the angular acceleration is also the velocity is equal to the radius times the angular acceleration. So these are the three equations you're going to need to know, and the rest of this process should be a piece of cake. I'll link where I got this method from in the description. Okay, so imagine you have an object moving around a circle, and as you know, in a circle, objects move around tangentially. But however, the magnitude of its velocity is unchanged, only direction. Therefore, consequently, we can infer that this v is equal to this v. So if we let this v1 equal v2, therefore v1 is equal to v2. And obviously the force is towards the center, but that's besides the point. And in between here, let this be the change in theta, just for the sake of argument. So now we can construct an isosceles triangle, with each side being the velocity. So here it's velocity, and this would be the change in velocity. And here it would be the change in theta. Now, imagine, let's say we wanted to find this v. So first we'd split this in half, and now using some trig, we can write that. We can write that the sine of, remember this is theta over 2 because we divide it in half, so the sine of theta over 2 would be equal to the opposite, which is delta v over 2 because it's divided in half, so delta v over 2 divided by v, which is the hypotenuse in this case. So now let's rearrange for delta v. So now we can write that delta v over 2 is equal to v sine theta over 2, and now delta v is equal to 2v sine of theta over 2. Or sorry, these are all delta theta. Now, in acceleration, what we're trying to find is the change in velocity. And if you know about math and derivatives, we want delta theta to be as small as humanly possible, or as in to approach 0. And we know that the sine, as the sine of x approaches 0, it becomes closer to just x, which you can see here. Blue is just y equals x, and red is equal to, and the red would be equal to sine of x. And you can see that as it gets closer to 0, then it equals x. So we're going to write now that instead of sine of theta over 2, we're going to write that delta v, instead of 2v sine theta over 2, we're gonna write it as 2v times theta over 2, and now the 2's cancel out. Boom, boom. So now we can write that delta v is equal to v times the change in theta. So recall this equation that I have highlighted over here. Since we know that, we can write that delta theta is equal to omega times time. Therefore, delta v is equal to v omega times time. And now finally, we can use this equation. And since we know that the velocity is equal to the radius times the angular velocity, you can write that omega is equal to v over r. Therefore, delta v is equal to v times v over r times t. Now this should be coming in. So now delta v is equal to v squared over r times t. Now a final reminder that acceleration is equal to delta v over t. So now delta v over t is equal to v squared over r times t over t. Obviously this will now cancel out. So now we finally reach our final expression. Therefore, delta v over t is equal to the acceleration, which is equal to velocity squared over